Okay, I think we can start. Welcome to this second day of the workshop. Today the program is particularly rich. We will have two talks in the morning and a discussion session in the afternoon and another talk after the discussion session. So the first speaker is Oscar Diaz, and he will talk about diving into the interior of asymptotically flat hairy black holes and maximal warm holes, which I guess is not a typo, right?
No.
Okay. Please.
Thank you very much, Paolo. Thank you to Paolo, to Massimo, and to all the other organizers for this kind of opportunity to be here. It's my first time in Florence, and of course, as you know very well, this is one of the most beautiful cities in the world. And also congratulations for your Galileo Galilei Institute, because it's a very good and excellent initiative. So today what I want to talk about is about what happens when we dive into the interior of an event horizon of an asymptotically flat black hole that has some scalar field condensate around it. And we will see that naively, what we would expect is that this solution, because it is charged, in the interior of an event horizon, we would also find a Cauchy horizon or a Wiener horizon. But what we will find is that when an observer dives into the interior of the event horizon and tries to approach the Cauchy horizon, we will find that this Cauchy horizon will not be there. Actually, it will be destroyed and replaced by a space-like singularity that is of the Kasner type, in the sense that it is described by an exact analytical solution that was found by Kasner, and that is usually called the Kasner cosmology. Okay? So this is based on work that I have done with Gary Horowitz at Santa Barbara and George Santos in Cambridge. I think that everybody knows these two collaborators, so they don't need presentation. I should also remark that after our paper, Mark Henault also published a very nice paper about this subject that deserves to be read and that I will mention. I will mention the main results. I think that it's not me, right? I'm muted. No, I'm muted already. Very well. So let me first start with some motivation for the work that I will present today. So the main question that I want to address today is what happens when we dive across an event horizon into the interior of a black hole. And this question raises many sub-questions, both at the classical and quantum level, and some of these questions have already been addressed, some others have not yet been fully understood. So let me give you an overview of some questions that are related with what happens when we cross an event horizon. So first of all, probably I should start by mentioning that in the 70s, as it is very well known, Hawking and Penrose have introduced the so-called singularity theorems that essentially tell us that at the interior of a black hole, or more generically in a cosmological setup, the space-time should always end at a singularity. However, Hawking and Penrose, they have not told us what happens when we approach this final singularity. This is something that Belinsky, Kalashnikov, and Lifshitz, the famous BKL trio of authors, it's a question that these authors have addressed. So basically they have told us that at late times, when we are approaching asymptotically a singularity, the solution near this space-like singularity is very elaborated, and it's always described by a Kasner cosmology. And in particular, when we are approaching this Kasner singularity, or space-like singularity, quite often we can have what is called the chaotic BKL oscillation behavior, which means that as we approach this singularity, at least in pure gravity, what happens is that the system goes through a sequence of Kasner cosmologies. So the Kasner solution is described by certain exponents, and what is happening is that these exponents, typically they are not fixed. There are transitions between different exponents as we approach singularity. And actually, in the case of pure gravity, these transitions, there is an infinite number of these transitions as we approach the singularity, and that's why it is called a chaotic behavior. On the other hand, related with this question of having a singularity in our space-time, let us remind ourselves that Garock and Horowitz in the late 70s also proposed the so-called weak cosmic censorship conjecture. That basically states that naked singularities should not form in nature from gravitational collapse. There is another set of questions that are related with what happens when we dive into the interior of a black hole that started by being addressed by Garock also in the 70s. So basically Garock, what he said is, let's look at the Rice-Nordstrom solution or to the Kerr solution. This solution, besides the event horizon, it also has a Wiener or Cauchy horizon. And at this Cauchy horizon, we know that predictability breaks down, meaning that giving initial data at a space-like hypersurface is not enough to predict what happens beyond the Cauchy horizon. Okay, so if we have basically, we have our, for example, we have the asymptotic past and the asymptotic future infinity. We have the future event horizon. Then we have here a Cauchy horizon. Okay, and if we prescribe initial data here, this is not enough to know what will happen. So I'm drawing here the Penrose diagram for Rice-Nordstrom or Kerr. So this is the origin. And here we have the Cauchy horizon, and we see that if we are somewhere here, in the interior of the Cauchy horizon, knowing data here, or more generically, knowing data along this null hypersurface, here and there, if you want, is not enough to predict what will happen there, because if I have information coming from here, I need it to predict what will happen there, but I can also have, for example, information that is coming from nearby this singularity, and that is not prescribed in this initial hypersurface. Okay, so predictability should, there is a question? Oh, like this? Is this enough? So what I was saying is that here, okay, perfect. So this question actually was addressed in more detail some years later by Penrose, that basically told us that Cauchy horizons indeed should be artifacts of symmetry, and they should not arise from generic initial data. And he also proposed a mechanism to avoid their appearance. Basically, he pointed out that there is something that we call the blue shift instability, also known as mass inflation, that should produce a singularity where the Cauchy horizon is expected to appear. So basically, the argument of Penrose was the following. So let me use this again. So if you have an observer, a time-like observer, in the outside, in the outer domain of communication, so outside the event horizon, you will necessarily approach I plus here. And now we can ask this observer, let me call it observer A, to send a set of null rays to the interior of the black hole. And now if we have a second observer here at the interior of the black hole, let me call it observer B, this observer will receive all these signals. But you see, these signals here, if observer A lives forever and kept sending periodically these signals, he will send an infinite number, you will send an infinite number of signals with finite energy. So it means that it will send an infinite energy to the interior of the black hole if he lives forever. But of course, it will take him an infinite amount of time to send this infinite amount of energy. However, the observer B, that is in the interior of the black hole, will receive these signals in a finite amount of time. Okay, so the energy density should blow up as he approaches the Cauchy horizon. And this is the so-called blue shift effect. Okay, And this infinite energy density that piles up as the observer B approaches the Cauchy horizon should make the Cauchy horizon collapse into a singularity. That was the main argument of Penrose. Ultimately, this led to the so-called strong cosmic censorship conjecture, initially formulated by Penrose and then reformulated by Christodoulou in 1999, that basically states that generically, meaning for generic initial data, the resulting solution can never be extended across a Cauchy horizon. Or said in mathematical terms, the maximal Cauchy development of a two-ended sigma should not be extendable. So this is the maximal Cauchy development of this hypersurface here. Very well, guys, let me just emphasize very quickly that although these two conjectures share, let's say, 3 words, this one is the weak conjecture, this is the strong conjecture, and they are not related okay? In particular, the weak cosmic censorship conjecture is not implied by the strong cosmic censorship conjecture. So let me give you here an example of a situation of a system that violates strong cosmic censorship, but not the weak cosmic censorship. So here what we have is, we have the origin, we have the past null infinity, future null infinity, and we have here an horizon. I have here some space-like hypersurface where I prescribe some initial data. If I'm on a point there inside the event horizon, I see that initial data prescribed here is not enough to predict what will happen there. So this is very similar to the situation that I described on the blackboard, because I can also have information that is coming from that region over there that is also necessary to predict what will happen there. So this is a case where we are violating strong cosmic censorship, but not weak cosmic censorship. On the other hand, in this Carter-Penrose diagram, we have a system that violates the weak cosmic censorship, but not the strong cosmic censorship, in the sense that this diagram is very similar to this one, but instead of having an horizon there, what I have is a null singularity. And now what happens is that clearly at any point here, giving the initial data there is enough to predict what will happen over there. But then we see that we have a naked singularity that is exposed. So it's violating the weak cosmic censorship. Okay, let me now give further motivation for what I will discuss later in this talk. This is this is now more directed to exactly what I want to discuss today. So let me refer to these works done in asymptotically anti-de Sitter spacetimes, where the authors try to understand what happens at the interior of a black hole. So in these papers, the authors started with Reiser-Nordström ADS. In Reiser-Nordström, it's still true that I have here the time-like infinity. I have here my past event horizon, my future event horizon, and then I have here the Cauchy horizon, okay? And then I have here the time-like singularity. So this is the kind of diagram that I represented here, but instead of having null infinity, I have the time-like infinity because I'm in ADS. And now what these authors called our attention to is that it is very well known since the holographic superconductor program started, that if I perturb this Reiser-Nordström ADS black hole with a scalar field, I know that Reiser-Nordström becomes unstable to scalar condensation. If the temperature of the system is below a certain critical temperature, that gives the critical temperature of the holographic system. And this is a computation that you do at the linear level. So you perturb linearly the Reiser-Nordström solution with a test scalar field that satisfies the Klein-Gordon equation. And you find indeed that the system is unstable. But then at non-linear level, you can also show that this scalar field that appears at leading order in perturbation theory back reacts on the gravitational field and Maxwell field, and actually they produce a full nonlinear solution that has a scalar condensate floating above the horizon, and this scalar field does not collapse because there is some electric repulsion that balances the system against self-gravitation. And this is what we call an airy black hole. because now you have this scalar air floating above the black hole. Now, this is something that we know since at least 10 years ago, when the holographic superconductor program started. Then what these authors did recently is that they decided to dive into the interior of this airy black hole, and they found that an observer that does so, he will go through 3 epochs. And remember that once you are inside the black hole, the coordinate r becomes a time-like coordinate, so it gives the arrow of time. And then they found that deep in the interior of the event horizon, as one approaches what should be the Cauchy horizon, what they found is that this Cauchy horizon does not exist. It is replaced by a Kasner space-like singularity. So instead, you have an observer that crosses the event horizon, tries to approach this Cauchy horizon, okay? And what they find is that actually instead of finding the Cauchy horizon, they will not find it, and instead they find a space-like singularity that is also known as the Kasner singularity. And they have also described the several stages the system goes through when it's approaching this final space-like singularity. So let me be clear here. The BKL work from the 70s already tells us what happens when we are approaching this space-like singularity, asymptotically, at late times, okay? But it says nothing about these pre-asymptotic phases, okay, the early times, okay? The BKL analysis does not describe those early times. These authors, they managed to see what happens through all the times, not only as we approach the final Kasner singularity. Very well. So, what do I want to do today? What I want to do today is to ask whether mutatis mutandis, because we are in the olden Roman Empire, so this is Latin. It means that, for those of you that might not know, this means that apart from small changes that might be needed, I want to ask if what the previous authors found for the ADS black hole also holds for asymptotical flat black holes. So I want to find whether the properties, the features of the system that were found in the asymptotically flat airy black holes, whether these features are universal or not. If they are very specific to asymptotical ADS black holes, or if they are quite a generic property of gravities, in particular in asymptotically flat airy black holes. Okay? And so, today I want to dive into the black hole interior of an asymptotically flat charged airy black hole. And I will follow the same steps that we did in ADS. So I will start with Rice-Nordstrom, asymptotically flat Rice-Nordstrom. I will add a charge scalar field, a test charge scalar field. I will find that the Rice-Nordstrom system is unstable to scalar condensation. Then I will say that this scalar that forms at leading order in perturbation theory can be back reacted on the gravitational field and Maxwell field to show that there is a full nonlinear airy black hole. Okay, this airy black hole, we will find that it has some properties that were not observed in previous airy black holes, in particular in ADS. In particular, there is a new class of airy black holes that we call maximum warm holes. Okay, and then this is part 1 of my talk. And then in part 2 of my talk, what I want to do is I will take these airy black holes, and I will dive into the interior of the event horizon of this black hole, and I will see what happens to an observer that does so when it tries to approach the would-be Cauchy horizon. And we will find that the system will go through a few stages that are similar to the ones the observer goes through in ADS spacetimes with small changes.
By dive, do you mean calculate geodesics in this space?
No, I mean that, no. I mean diving generically. It does not have to follow.
What does it mean?
It means crossing the event horizon.
Yes, but what is the calculation that you do that corresponds to the word dive?
Oh, it means that I will I will take an ansatz that where my coordinates will run.
So you look at the geometry.
I look at the geometry, the Maxwell field and the scalar field. I will plug these ansatz in the Einstein equations or Einstein-Maxwell scalar equations, and then I will solve the Einstein-Maxwell equations or scalar equations.
Okay, thank you.
There is another question.
Is this instability related in any way to super radiant instability of charged black holes?
I will describe it. No. It's related with the violation of the BF bound, the two-dimensional BF bound in the near horizon region. I will discuss it in detail. Although this, okay, but anyway. Okay, so part one of my talk, I want to discuss my theory and the black holes of the theory and their properties. So let me start by specifying the theory. My theory is an Einstein-Maxwell theory with a charged scalar field, where this charged scalar field has a specific coupling to the Maxwell field. So I have the Ricci scalar, I have the Maxwell term, I have a kinetic term for my complex scalar field, I have a mass term for my scalar field, and now, in order to have airy black holes in the theory, I need to add this scalar Maxwell coupling. So you have f squared times the scalar field square. Okay? This is fundamental in order to have scalar condensation. So in ADS, you can trap a scalar condensate because you have the ADS gravitational wall, okay, that traps the scalar field inside. But for an asymptotically flat solution, if you put some wave, some scalar field wave around it, this scalar field wave typically will die off at infinity. It will not get trapped. There are no bound states. In order to have these bound states, to have this gravitational potential wall, I need to introduce a term like this. I could also introduce something, another kind of potential, for example, a self-interacting potential that besides the mass term also has cubic or fourth order terms, also does the job. However, in that case, the airy black holes that appear, they are not connected to the Rice-Nordstrom in the sense that there is no limit. In the limit where the scalar field goes to zero, the amplitude of the scalar field goes to zero, the airy black hole does not merge with the Rice-Nordstrom black hole. And I would like, in order to study the interior of the black holes and make it close to the Rice-Nordstrom, I would like to have a black hole, an airy black hole, that in a certain limit approaches the Rice-Nordstrom black hole. That's why I'm using this particular term in the action. Okay? Now, first, what I want to do is to study the solution in the exterior of the event horizon.
Thanks. Can you, where does this come from? Like, does it come from any, can you embed it in some supergravity or?
No. This is a toy model.
You just invent this because you want this feature?
Yeah, we just cooked up a theory, the simplest possible theory we could think of, that would have bound states to trap the scalar field condensate. Okay? In an asymptotically flat case. Okay? And then the idea is that hopefully, you know, the properties that we will study are universal enough that if then you come from top-down approach, you will also find this kind of solutions.
Okay, just a question. So essentially, you can interpret this term you added by hand in two ways, either as a modification of a coupling constant, because it renormalizes the factor in front of f, or a changing of m. So if you interpret it as a coupling constant which is changing, you could think of using a dilaton. Have you thought about it?
No. This is a special case if you want. For the dilaton case, this coupling would be an exponential one, right? It would be, instead of having phi square, you would have exponential. Look, this is one possible toy model. I'm not saying that there are no other ones.
No, okay.
It will be pretty clear why am I adding this.
Actually, Oscar, sorry, I had a related question that maybe it's I don't know if it's simple or not, but another toy model, maybe it's related with this question, could be taking a neutral scalar field and a no-minimal coupling with a squared. And in that case, there should be hairy black holes as well. Like an exponential coupling in front of f squared or a phi squared f squared and a neutral scalar field.
In that case, and for example, yes, in that case you can have, and it will also form a Kastner singularity in the end of the day. And actually, using the BKL approach, you can see that at late times that does happen. So I'm not saying that this is the unique model. I'm just saying this is a model where this happens, and hopefully, this is what will happen here. Qualitatively, will also happen in other cases. So the key point is you want to have scalar condensates at a non-linear level. And I will make this very precise, what I mean by this in the next slide, okay? So just give me a minute and I will get there, and then you will see. Now I can cook other theories that do the same job. So in order to study the solutions, at this point, I'm just concerned outside the event horizon. In the outer domain of communications, I need an ansatz. So I propose this static spherically symmetric ansatz. I'm working here in the gauge where the entropy is proportional to r squared. And of course, this theory with this ansatz has a well-known solution, that is the Rice-Nordstrom solution. In this case, there is no scalar field. And we know exactly what is this solution. It is parameterized in terms of r plus, which is the event horizon radius, and in terms of the chemical potential, so that the charge is the chemical potential times r plus. Yeah, but I can set the scalar field to 0, and I find that the Rice-Nordstrom is a solution. So, yeah. So it's a special case where the scalar field vanishes. Okay. Now, one thing that I can do, I can introduce now a test scalar field around this Rice-Nordstrom solution. It will satisfy the Klein-Gordon equation of the system. Of course, when I say Klein-Gordon, I have to be careful because the Klein-Gordon originally does not have this term. But anyway, I can linearize the equation for the scalar field. And I get a certain ODE after I use Fourier decomposition a long time, because dt is a killing vector field of the background. This introduces me the frequency of the perturbation. And what I find, so this is a radial ODE. I can study this radial ODE asymptotically, see what is its behavior. And I find that these solutions, as long as the charge of the scalar field times the chemical potential is smaller than the mass of the scalar field, I find that the scalar field decays exponentially at infinity. Of course, here I'm killing already the second linear independent solution, which is one that grows up exponentially at infinity. So there is an exponential decay at infinity. And this exponential decay is characteristic of a bound state. This is the potential gravitational wall that will trap my scalar field. Now, you can cook up other theories that have also an exponential decay at infinity that creates the conditions for bound states. And there will be other theories that do the job, okay? Otherwise, if the charge times the chemical potential is bigger than the mass of the scalar field, what happens is that the scalar field, instead of decaying exponentially at infinity, will oscillate at infinity. And this in particular means that it is not bounded to the black hole. You can compute the energy, you will find that the energy will be infinite. So you want to discard such solutions. So from now on, I will concentrate on this case. Okay? Now, coming to your question, what is the origin of this? So I will say that this system, when I solve it, I will find an instability. Let me explain the origin of this instability. The origin of this instability can be understood by looking to the near horizon of extremal Rice-Nordstrom. So Rice-Nordstrom has a particular configuration that has 0 temperature. That's what we call the extremal black hole. And this happens when the inner horizon approaches the outer horizon, the event horizon. Now, in this limit, you can apply this near horizon coordinate transformation. So you see that you are zooming around the event horizon. Okay? So you do this coordinate transformation where lambda is a parameter that you send to 0. So that you are literally zooming around the event horizon in the end of the day. And what you find when you do this is you find this new solution. okay? Where this new solution, you see that it's a direct product of ADS2 cross a two-sphere, where the radius here is fixed. Now, the nice thing is that here, you are literally just picking the leading order term in this expansion in lambda. However, this is still a solution of the original action. Okay? So this is what we call the near horizon solution of the extreme horizon Austrian black hole. Sometimes it's also called, or sometimes no, in the old days it would be called the Bertotti-Robinson solution. Okay? Now, what happens here is that you can also apply this coordinate transformation to the original Klein-Gordon equation, or if you prefer, you can solve now the Klein-Gordon equation directly on this geometry. And what you will find is that, in the end of the day, this Klein-Gordon equation will have an effective mass. This effective mass is no longer this mass in the full geometry. It is this m square minus now a term that comes from the electric charge of the solution. So the story here is very similar to the one of the holographic superconductors in ADS. Now what happens is that although you start with a positive mass in the asymptotic region so that the theory is well defined, it might happen that because of this minus sign, it might happen that in the near horizon region, you will get a mass that is negative, and in particular because you are in ADS, it's negative and below the so-called ADS2 Britt-Lohner-Friedman bound. Now, if this happens, we know that this region, this near horizon region should be unstable, okay? Because you are below the ADS2 BF bound. So somehow, asymptotically, the geometry should be okay, because the mass is positive. But in the near horizon region, something should be wrong. So this system should evolve towards a new solution that keeps the same asymptotic, but changes the near horizon region so that it no longer violates this bound. But before arriving there, let me just present the linear results.
Sorry, I have a question. How come that omega does not enter into the asymptotic behavior at large R? I would expect the radial momentum to be omega square minus m square.
No, it does not appear.
How come? I mean, take the derivation and put R very large. It's the radial momentum is omega square minus m square. So you're looking at omega equal to 0.
No, you mean here?
No, above.
Above. No, there. Now there I'm looking at the static case. Yeah, exactly. So I'm considering what will happen. What are the conditions then to a nonlinear level have a static spherically symmetric solution? Yeah, but at linear level you can also do the analysis. You keep omega different from 0, and you will get still an exponential behavior. Yeah. So.
Sorry, I have a small question. I was rethinking the model. I have a question. Whether this analysis is stable under the inclusion of an R psi square coupling?
You mean this one? This term here comes?
No. Your action at the beginning. No, I mean you're adding terms which are higher order in derivatives.
No.
Or not? No, you have F square. Yes, okay, but here can't you add also a psi square R term? That would be, let's say, equally.
Most probably yes, and some.
But you have not analyzed this.
But I'm not doing that. I'm doing the simplest possible model where this can happen. Again, I'm not saying that.
So not all, let's say, not all natural. No. Two derivatives coupling.
No. This is the simplest toy model where this can happen. Okay.
Thanks.
Sorry, Oscar, just one question. So is this the same framework of an old...
Sorry, I cannot hear him.
I was asking, is this the same framework of an old Gubser paper before the holographic superconductor? It's the same.
It's the same spirit. Okay. You know, in Gubser papers that led to the holographic superconductor program, you also have a violation of the ADS2 BF bound that is responsible for the existence of the airy black holes.
Can you go back to the previous slide? Previous.
The previous?
So what's happening when 1 plus 4 phi psi square become 0? I think depending on value of psi square and alpha, kinetic term of Maxwell field become 0, right?
I did not understand, sorry.
Are you assuming alpha is positive?
Alpha is positive?
Yes.
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 I think there are solutions only for one. The negative mass comes from the kinetic because the m square is half of f square. So we get the negative mass.
It's essentially because of this term, q square. Okay, let me move on or else I will not finish my talk for sure. So let me just say that all this discussion about, the potential room for the existence of an instability due to the fact that you can have a violation of the ADS2 BF bound, indeed holds once you do a full numerical analysis of the Klein-Gordon equation on this system, and you indeed find that there is an instability. Okay, and this instability, so what I have here is, here I have extremality. That's where my argument of the ADS2 BF bound violation holds. And I see that indeed the imaginary part of the frequency is positive, which means that there is an instability. And then naturally, as I move away from extremality, this instability is still present all the way up to a certain region that is, or surface, that is this red surface. This red surface is when the imaginary part of the frequency goes to 0. So this is the onset of the instability. And basically at this red curve, what happens is that you really, at nonlinear level, that's where the area black holes will merge with Rice-Nordstrom, because this is when the amplitude of the scalar field will go to 0. Okay? So now what I want to discuss is what happens at nonlinear level in perturbation theory when I consider the back reaction of this scalar field in the gravitational and Maxwell field. And there what I find is that numerically, again, solving exactly the nonlinear equations, I find that indeed there are area black holes, static spherically symmetric area black holes. I can represent them in a phase diagram. Here I plot the mass of the solution. Here I plot Q minus M, so that this horizontal line at Q equals to M is the extremal configuration of the Rice-Nordstrom black hole. Rice-Nordstrom black holes exist for Q smaller than M, so they exist in this green region below. Then here this blue curve is the onset of the linear instability, and this is where non-linear area black holes start existing. Exactly at this blue curve, they coincide with the Rice-Nordstrom black holes because the scalar field condensate goes to 0. But then as I move up, what happens is that the amplitude of the scalar field is increasing. Now, what is interesting in this solution is that we would expect that at fixed M, if I go up and I increase the charge of the black hole, I should reach a configuration that is extremal and at 0 temperature. Extremal because the entropy goes to 0. So if you want, you get a naked singularity. And this is indeed what happens for small masses, let's say for masses smaller than 0.8. These area black holes exist all the way up to this extremal black hole configuration with T equals to 0 and entropy equals to 0. Now, the surprise that does not happen in other systems, for example, in the holographic superconductor systems, it does not happen, is that for masses above 0.8, these area black hole solutions exist up to this red curve. But this red curve represents a solution that is not singular, because the entropy is not going to 0, and moreover, the temperature does not vanish. So in that sense, we will call these maximal walls because they have maximum charge, right? The charge is going up. But they are warm, meaning that the temperature is not going to 0, unlike what was happening there. So there is some temperature in the system. Okay? And then area black holes stop existing. And the reason why these area black holes stop existing there is because you remember that there was this bound state condition for the existence of bound states. And above this curve, this bound state condition starts being violated. So black holes cannot exist above it. There's a question there.
Have you thought about what the implication of this to the weak gravity conjectures?
That's a good question. No,
Thank you.
We have not discussed too much. We have thought a little bit about
because this means that there has to be something that goes wrong here, right?
Not necessarily. Not necessarily.
Okay, but
yes, but it has implications. It has we can discuss them. Okay. Yeah, let me not divert here, or else. Very well. Let me move on. I'm really delayed now. So let me, before moving on, let me tell you why these maximum warm holes exist in this particular theory, but not in other theories that we have discussed up to now. So this is the first example of a maximum warm hole. The reason why this happens is that at fixed M, when we are increasing the mass, increasing the charge, sorry, the region here, the horizon, behaves typically like a standard black hole with scalar air. And so we would like to become singular, very much like it happens here on the left side. However, if the mass is large enough, as I told you just before, one reaches a situation where the asymptotic bound state condition that I mentioned before is saturated, okay? And the system cannot support scalar air if this bound is violated. So although the system would like to still exist, the point is that there is no longer a gravitational wall, if you want, that can bound this scalar air inside. And therefore, the solution stops to exist, okay? And we terminate at a non-zero temperature black hole, okay? Very well, now let me move to the second part of this talk. So what now I want to do is, having established that we have an area black hole in the system, I want to ask now what happens in the interior of it. So I literally want to send an observer across the event horizon. I don't care anymore about what happens outside the event horizon, because that I already discussed. And now I want to see what happens when I saw it inside the event horizon, and I send the observer towards the would-be Cauchy horizon. And for that, to study the black hole interior, I will now use a different ansatz for my solution. The radial coordinate that now becomes time-like in the interior of the black hole is now Z, such that infinity it's at Z equals to 0, the event horizon it's at ZH, and would-be Cauchy horizon or winner horizon will be at a larger ZI. Okay? So here you would have the infinity, then here you have the event horizon, then you have the winner horizon as Z is growing. Okay? And now plugging these ansatz in the equations of motion, I find that after some rearrangements of the equation of motions, there is one equation of motion that is of this form. The partial derivative with respect to Z of a certain quantity, C1, must vanish. Of course, this means that this C1 must be a constant along Z. And this C1 is specifically given by this expression. Now I will assume, and this assumption comes from the fact that without the air I have the Rice-Norton black hole where this happens. I will assume that there are two horizons, the event horizon and the winner horizon. And of course this F vanishes at both horizons. Moreover, I know that when I'm inside the event horizon, in between the event horizon and the Cauchy horizon, I know that F is negative, and I also know that the derivative of F at the winner horizon is positive. Okay?
Which is the symmetry associated with this charge?
What is the symmetry associated?
With this charge.
The symmetry associated with this charge. I don't think I can give you a good answer for it, except that this literally follows from the equations of motion. Yeah, I never thought about that. Let's discuss it in the end. Now the equations of motion also imply, this is a second consequence of the equations of motion, imply that the scalar field must vanish at the horizons. Okay, so this means that where I have here 5, for example, this term will vanish precisely at the horizon. So if I'm at the event horizon, I can show that in the end of the day, this C1 equation is given only by a term like this one. And a term like this one is necessarily negative. So C1 is negative at the event horizon. On the other hand, at the winner horizon, it's still true that phi is equal to 0. But this time, because here I have an integration from ZH to ZY, this term no longer vanishes. It vanished there, but not here. Okay? And now let's remember that the derivative of f, in this case, at the winner horizon, is positive. Okay? So in the end of the day, I can show that this C1 is positive. So at the event horizon, this C1, at the event horizon, this C1 is negative. At the winner horizon, this C1 is positive. But on the other hand, I know that C1 must be a constant. So this leads me to a contradiction. And basically, this contradiction is telling me that my assumption, my original assumption that there should be 2 horizons in the solution cannot be valid. So somehow, the winner horizon cannot be present in my solution when I have a scalar field. When I have a scalar field in my problem. So this, if you want, is a theorem that says that there can be no winner horizon in the presence of a scalar field. So I already know this.
Sorry, okay. Is it it was singular at large?
So this is valid for any area black hole.
Black hole, okay. But then what happens? I mean, how can the temperature be 0 on the left side?
When you have the temperature goes to 0, you don't have the event horizon. You have a naked singularity.
Okay, so in that case, the horizon is singular.
Non-zero temperature. Yeah, away from extremality. Otherwise, you have a naked singularity, and so this assumption fails immediately. Okay? There is another question.
About if you want, the imaginary part of the scalar field, you set to 0.
No, we are working in a gauge. I can always do a U1 gauge transformation that sets the scalar field to be a real scalar field at the expense of changing also the U1 Maxwell potential.
Okay.
Okay. So I'm working with in a gauge where the scalar field is positive and the Maxwell field goes to 0 at the event horizon. Very well. So having established that, I already know from the very beginning, without doing more than one slide computation, I know that the solution with scalar R cannot have a Cauchy horizon. Okay? But naively, I start with Rice-Nordstrom that has a Cauchy horizon. I put a little bit of a scalar field. I would not expect the Cauchy horizon suddenly to disappear, but I know that it will. So now I would like to see what happens. How does it disappear? Okay, and that's what I'm going to do next. So we will find in the next slides that the would-be winner horizon will be replaced by a Kasner space-like singularity as Z approaches infinity. In this process, an observer that crosses the event horizon will go through 3 main epochs that we will call the collapse of the Einstein-Rosen bridge. So he crosses the event horizon. Initially, he will go through this red region very fastly, if you want. And this red region encompasses the collapse, what we call the collapse of the Einstein-Rosen bridge, the Josephson oscillation region, and then it will enter into a phase that is called the Kasner cosmology phase. And eventually, some solutions for some initial data, we will find that sometimes this Kasner cosmology will have a transition to a new Kasner cosmology at late times. Okay? So in the next slides, I will describe in detail these 3 epochs. Okay? So first of all, what we will need to do is to solve the equations of motion. There are 4 equations of motion. basically two equations of motion for the gravitational field, one for the Maxwell field, one for the scalar field. Of course, they are nonlinear and coupled, okay? And the point is that in our study, we do a numerical study, but at the same time, we also do an analytical study. What do I mean by an analytical study? Of course, I cannot solve the original equations analytically, or else I would not do numerics at all. What we will do is the following. We will solve the equations numerically, and then we will also look into our numerics, we will look to terms in my equations of motion that eventually can be dropped. Meaning that if I drop certain terms in my equations of motion, I see that what I call the mutilated equations of motion without those terms still give a solution that approximates well the numerical solution of the full equations of motion. Now, the advantage of working with these mutilated equations of motion is that these mutilated equations of motion can be solved analytically. So I can also have an analytical expression for my fields. Okay, and of course we do this game always comparing the approximation with the numerical analysis to see whether, you know, the approximation is indeed good. Okay, so we always check for self-consistency. Okay, now it also happens that the three epochs and their approximate analytical solution is more cleanly identified when the scalar field is small. Scalar field being small means that I'm nearby the onset of the original instability of Reiser-Nordstrom. So the amazing thing is that you don't need a big scalar field to destroy the Wiener horizon. A small scalar field, no matter how small it is enough to destroy the Wiener horizon. And it just happens that in this case, that's where the analytical approximation actually works better. So this is good for us. So let me give you an example. During the first two stages of that my system will undergo, we can numerically verify and a posteriori justify that the mass terms, that this term, so these mass terms and this, or these mass terms and this charge term in my equations of motion can be
just to
dropped.
understand, you are saying that it is not an analytical in psi, the solution. Essentially, because if you send psi to 0, you have the inner horizon. As soon as you move a little away, you haven't, so you get some solution which is...
That's amazing. That's amazing. That's what happens.
Okay.
That's what happens. You know, again, if you have doubts about that, you know, this is something that you can check in 2 minutes, the theorem that I gave you here. Well, you would need to double check that I'm not misleading you when I say that the equations of motion imply this.
Yeah. But I mean, I think a way to see this is that there is an instability, and therefore, if it is triggered by a small scalar field, it will develop a scalar hair. It's a process that is called black hole scalarization, and it occurs in several theories.
No. What he's saying is that this is kind of a non-perturbative effect in the sense that at psi equals to 0, you have a Cauchy horizon.
Okay.
As long as you turn it a little bit, you would expect continuity. Yeah.
But it can be understood perturbatively, right? I mean, to leading order, you will have quasi-normal modes which are unstable.
Yeah, that's true. But on the other hand, the outcome is not continuous at all, right? Yeah. You go from a Cauchy horizon to a space-like singularity.
Yeah. Right.
You know, as long as you switch psi. I agree. This is quite impressive. Yeah, but again, you know, you don't need to do this. If you don't trust the numerics or these mutilated equations of motion, just go through this. This proves that there can be no Wiener horizon when you assume the existence of a scalar field. So something must happen, you know, and this is just turning a little bit of scalar field. Very well. So how much more time do I have realistically, Paul? Really, 5 minutes?
Well, yeah, we had a lot. We want to have
Okay. Well, I will have to go a little bit faster. Okay. So let me describe. Immediately after crossing the event horizon, I go through epoch number 1. So let's remind ourselves that naively, because this is a non-extremal solution, what I expect is that when my solution approaches the Cauchy horizon or any other horizon that is non-extremal, I would expect GTT, the time-time component of the metric, I would expect it to vanish linearly in R minus R minus, okay? But what happens in our system is that we find that GTT, as it approaches the would-be winner horizon, as Z is increasing towards infinity, we find that it is not vanishing linearly, but instead it's vanishing exponentially. The scale, we will see, that's the scale of, in the end of the day, it will be the Kasner exponent. That is the scale of the... it is a dimensional, yeah. Yes. I will give you later. Can I give you later? So we see that GTT is following exponentially fast. And by the way, here the solid line is the solution of the full nonlinear equations of motion, the numerical solution. And the dashed line is the solution of the mutilated equation of motions that we can find analytically. Okay, so this is showing that indeed the analytical solution is a good approximation to the numerical solution. By the way, we can also plot the scalar field, of course, and the other fields. Okay, but these are integration constants of my problem. Okay, you have a second order linear system, so when you do integrations, you will have some constants, integration constants in your system. Yes, it's over there. Yeah. Say it again, sorry.
The original action is actually valid during this exponential. The question is whether the initial action is valid during this exponential decay. Whether.
Why shouldn't it be?
Because it can have large derivatives. Depending on the scale of the exponential decay and the oscillation, you can have large derivatives. And if you have large derivative, it means that your original action is no longer valid there. No, but it means that there are corrections, higher derivative corrections, that you have to take into account, typically, right? So what I'm asking is, classical or...
Guys, can we discuss this after, or else I will not finish my talk. This direction. Guys, then we enter the second epoch. During the second epoch, what happens is that the derivative of the Maxwell field becomes extremely small. And so this means that when I go back to my equations of motion, the terms that involve the derivative of the Maxwell field, I can put them to zero. I can neglect them. And this allows me to solve analytically the equations of motion. And I find that the scalar field obeys a Bessel function equation. And therefore, the solution is given by Bessel functions. This is what we call the Josephson oscillation. So my scalar field will oscillate many times during this epoch. And again, here you can see, if you pay really attention, you can see that there is a solid line, that's the numerical solution, and then there is the dashed line that is exactly on top of it, which describes the solution of the mutilated equations of motion, where I have discarded these terms besides discarding other terms. And by the way, of course, this scalar field back reacts on the metric, and basically, if you compute a certain quantity that is related with GTT, you will see that these many oscillations, they produce this zigzag function on the gravitational field. Okay, and again, you have the numerical solution against the analytical solution. And then what will happen is that after a certain time, that you can already see it here. Oh, sorry. Oh. You can already see it here. You can see that the scalar field is growing in time. The envelope of the scalar field is growing in time. And actually you can see, looking to the equations and to the solution, you can see that it's growing logarithmically in time. Now, if it is growing logarithmically in time, this also means that the gravitational fields, they are growing polynomially in Z, okay, in time. And this means that the solution will start being well approximated by the Kasner solution, the Kasner cosmology solution. And in particular, you can see this very well if you introduce the proper time coordinate, that is basically the integral of G Z, that goes as a polynomial of Z. And then you see that your geometry is described by this solution here. So you have psi growing logarithmically in time, and then you see that the metric coefficients, basically, they grow polynomially in time. So this is literally the Kasner solution, or the generalized one to have a scalar field. And these exponents that appear here, they are precisely well known. You know very well what
just
they
a question. Kasner cosmology is associated with an empty space-time. Yes.
That's why I'm calling generalized.
But all your exponents are satisfying the Kasner constraint. So it is an empty cosmology. But you started with...
No, it's not an empty cosmology. It has also the scalar field. Yeah, and you know, in particular,
well, but with those Kasner coefficient, the rich scalar is identically zero. So you have an empty cosmology.
No. Yes. That should not be the case, because you have this.
Well, but with those coefficient in front of...
if you put this
No, with those exponent of Kasner...
This one?
No, with the p's you are using, you are satisfying the Kasner constraint, aren't you? Because the sum of the p's is equal to 1, and the sum of the squares of the p is equal to 1. Okay, so you are in a Kasner cosmology. Yes. The Kasner...
Yeah, there is...
No, no. Yes, okay.
You know, this is the original Kasner when psi is 0.
Okay.
Okay? That's why I'm calling it generalized, you know. Now this time it also has a scalar field. This scalar field also has an exponent. This exponent enters on this constraint for the exponents. You know, but this is known, you know, this solution is known. I think that Kasner, even in the original paper, already discussed the this case in the end of the paper. If he does not, someone immediately after did it. So this solution is very well known. We are not introducing it. Okay.
So since we are a bit over time, I will just let Oscar finish the talk, and then we can discuss later.
Thank you, Paulo. Now, what is important here is that if you look to this solution, and you compute, for example, the Kretschmann curvature, you will find that there is a space-like curvature at t equals to 0, at tau equals to 0, which corresponds to z goes to infinity. Z goes to infinity, that's where the Cauchy horizon would be. So you see that the would-be Wiener horizon is literally replaced by a space-like Kasner singularity. Okay? And GTT is decreasing exponentially as we approach this Kasner singularity. Now, this is true when beta, this beta that appears there, okay, is bigger than 1/2, which means that the Maxwell field is smaller than 1, much smaller than 1. Now, what can happen sometimes for some initial data, and I will have to be very quick here, is that sometimes beta can be bigger than, smaller than 1/2. Because if you this beta, actually we can compute beta as a function of Q over QC. QC, that's where the onset of the instability, if you want, is the critical charge or the critical temperature, if you want to think in terms of holographic superconductors. And this beta depends, it's very sensitive as a function of Q. A little change in Q can change beta really a lot. And in particular, you see that we can also have situations when beta is smaller than 1/2, or beta square is smaller than 1/2. But when beta square is smaller than 1/2, actually GTT, instead of decreasing exponentially, it's increasing. So it's the opposite of what we were describing till now. What happens in this case is that when this happens, the Maxwell field is no longer small. So it will start back reacting on the gravitational field and on the scalar field. And it reacts in such a way that it induces a transition in the system that change beta from something that is smaller than 1/2 to a new beta that is bigger than 1/2. So we go back to a situation where GTT is decreasing exponentially to 0. Okay? So these are the so-called Kasner transitions. So the system does not have to end up immediately in a final Kasner cosmology solution. It can sometimes make a transition to a new Kasner solution, then another one can have a finite number of transitions. Actually, it's also true that in some cases, for some fine-tuned initial data, it can also have an infinite number of transitions. Okay, and this leads to what is called the chaotic BKL oscillatory behavior. So in pure gravity, you always have an infinite number of transitions. In this case, when you have this scalar field, typically you have a finite number of transitions except for a set of measure 0 initial data. Okay? All these findings that I'm describing here are in agreement with the theorem that we established a few slides ago, that there can be no winner horizon when psi is present. A tiny psi automatically destroys the winner horizon and replaces it by a Kasner singularity. And so this is basically what I wanted to say. So let me recap very quickly. So I have told you that, at least in the theory that I gave to you, airy black holes can terminate on non-singular black holes because the entropy is not 0, that have a maximal charge but non-zero temperature. We call these maximum warm holes. And then what we have shown is that when we dive into the interior of these airy black holes, an infalling observer goes through 3 epochs, and in the end of the day, the Cauchy horizon gets destroyed and replaced by a space-like Kasner singularity. I should also very quickly, and then we can discuss this a little bit, the late time stages of the theory can be understood without doing any numerics and actually just by solving ODEs. And this is what BKL did already many years ago. For generic, you just need the action, you don't need further details, you don't need to plug and solve the equations of motion for this. And this BKL dynamics actually also have a cosmological billiard description that is really nice because it corresponds to having a billiard table, literally, on an hyperbolic space. And then, the geodesic motion of a ball on this table and the bounces when it hits the borders of the table, they correspond to Kasner transitions. So every time that the ball hits the boundary of this table, it makes a transition to a new Kasner cosmology. Now, what happens in pure gravity is that the volume of this table is infinite. So the walls, if you want, are infinitely far apart. So you see, sorry, it's the opposite. So what happens, when you have the chaotic BKL behavior, what happens, you have a finite volume, and this is what happens in pure gravity. In our case, what's happening is that in this cosmological billiard description, one of the sides of the table is missing. So the volume becomes infinite. So this means if you have a ball inside this table, it can hit one of the boundaries. There is a transition to a new Kasner cosmology. It can hit another one, there is a new transition, another one, there is a new transition, but then it can escape to a region where there is no boundary. And then it means that the system went through 3, for example, Kasner transitions, and then it stabilizes and stays, in that final Kasner cosmology until it reaches the space-like singularity. And I should stop here.
Thank you very much.